Hi class, so this chapter is chapter 5.5. We're going to look at some medical applications using radioactivity, radioisotopes. So if you look at this first picture here, this is a woman laying down and there is a scanner over her neck. She has a radioisotope in a specific organ and the scanner is picking up the radiation. From there, there's instrumentation and an image of the organ will be projected and they can determine what's going on with that. So this is how we use radioisotopes in medicine. Radioisotopes, last section we covered is that there's half-lives. There are radioisotopes that have very, very long half-lives and some that are very, very short half-lives. In medicine, nuclear medicine, they want radioisotopes with very short half-lives. You would think that the body would be able to detect a radioactive isotope from a non-radioactive isotope, but that's not true. The cells do not differentiate between it. So let's say if your body needs iodine, it's going to pick up iodine whether it's radioactive or not. It's not going to reject it. Once it's incorporated, it will travel to where it needs to be in the organ, and that radiation can be picked up by a scanner, and then proper instrumentation will get it to an image, and then it can be looked at. And because these radioisotopes that are used have a short half-life, they decay very quickly, depending on what part of the organ they're used in. So here is some radioisotopes and the half-lives and what they are where they're used in the body. So let's just take a look at a few of them here. We have gold-198. Half-life is 2.7 days. This is beta radiation, and it is for liver imaging and treatment of abdominal carcinoma. And then we have bismuth-213, 46 minutes. That's not even an hour. That's quick. This is alpha radiation, treatment of leukemia. Let's see if we can find one down here somewhere. We have iodine-123, 13.2 hours. This is gamma, treatment of thyroid, brain, and prostate cancer. So you can see that there is different types of, the amounts of half-lives are different, but it's based also on where it's going in the body and what type of radiation. You can see all of these are radioisotopes, radioactive isotopes. Here are more. Here, again, different half-lives. There's days, there's hours. This is 6 hours for this one, imaging. Treatment of liver cancer here, 2.7 days. Okay, so scans with radioisotopes. So after the radioisotope is ingested, the scanner is going to go over that organ where the radioisotope is at. And the scanner is going to pick up that the level of radiation. So it's going to be able to, one, locate to make sure the radioactive isotope is where it needs to be, and then determine the amount of radiation coming from it, and all that information will be depicted into an image, and then they can go from there. Gamma rays emitted from radioisotope can be used to expose a photographic plate and produce a scan of it. And here's a picture of a radioactive isotope in iodine-131 in the thyroid. So positron emitters have with short lives can be used to study brain function, metabolism, and blood flow. These involve carbon-11, oxygen-15, nitrogen-13, or fluorine-18. And here is just, remember we were covering balanced reactions. They have to balance on both sides. There's 18, 18 plus 0, and 9, 8 plus 1. Remember, a positron emitter, remember the word pos means it's positive, but it's the opposite of electron, so it has a plus 1 here. They combine with electrons after emission to produce gamma rays that are then detected by computers. So these are all this, they may be different types of radiation, but they're pretty much all specifically used that they can eventually end up that information in a computer, and an image is created of whatever organ or body part that needs to be looked at. So here is positron emission tomography. This is PET. They usually call these a PET scan. This is a PET scan of a normal brain on the left and a brain affected by Alzheimer's disease on the right. You can see there's visible differences here. You can see that the blue here this one has a lot more blue here. This is all intact and this is separated. So that might be, your book doesn't go more into that, but I wish it did, so it would explain a little bit more on some of this stuff. And then we have a CT. Some of these words are probably you've heard over and over again somewhere. If you watch TV, medical shows and medical, dramas, they bring up a lot of this stuff. Here is an image using a CT scan. So this can scan or brain, lungs, heart, and it's a computed tomography. Computer monitors the absorption of 30,000 X-ray beams that should not have cut off, directed at the brain in successive layers. So what it sounds like is it takes non-stop beams, and these beams, the length and radiation, not radiation of it, the beams somehow compute back into a computer, and it's able to give layers. So it doesn't sound like this is a flat. This might be more of a 3D kind of thing. Don't really know. Your book doesn't really go more into it, and me being a chemist, I really don't know more than what I'm giving you in the book. Differences in absorption based on tissue densities and fluids provide an image. Yeah, so basically the densities and allow more of a 3D to give an image if there's something. So it basically, what it sounds like is it can pick up the densities, and it's able to transfer that information into a CT scan. Is what I'm trying to say, and I'm starting to get tongue-tied. MRI, magnetic resonance imaging, that does not involve nuclear radiation, so this does not involve radioisotopes. Least invasive of all the imaging, it's based on the absorption of energy when protons and hydrogen atoms are excited by strong magnetic fields. Works because the energy is absorbed is converted to color images of the body. And here's an MRI. It's got a bunch of colors here. This is of the heart and lungs. All right, so which of the following radioisotopes are most likely to use in nuclear medicine? Well, we want ones that are short. So right off the bat, you can tell that A is not going to be, off the top of my head, I think that's 1.3 billion. So we don't want something in there. The isotope will last longer than we will live. That's out. But B is decent, 12 hours, and C is decent. We saw some of these hours in days in what we were looking at. So B and C would be more than fine. So yes, A, not likely, way too long. Short half-life for B, probably used, and C, short half-life, likely used as well. So chemistry, so this is again another fancy word that I probably am not saying right. Brachytherapy, the process of brachytherapy is seed implantation. There's two types, they're permanent and temporary. This is prostate cancer. So this is a permanent brachytherapy procedure. It is, so this are, I found this picture online, and you see these seeds here. I was reading about them, and they say they're about the size of rice, the little rice seeds, and they're implanted into where the tumor's at in the prostate. And this does not look comfortable, but it has to be done. You know, these things are important. Utilizes radioactive iodine 123, palladium 103, or cesium 131 in the seed, and they decay, and they will, as they decay, they will give off gamma radiation. So the radiation will kill the cancer by interfering with the reproduction cancer cells with minimal damage to the adjacent normal cells. Now, it doesn't talk about the half-life, and it did, I believe, talk about that in the reading. I cannot tell you right now. I did read this, but they're not, they stay permanently, but they do not affect the body after so long. So they are purposely placed. They are not removed, but as they decay, and I'm pretty sure these are pretty fast, once they're decayed, they just stay there, and that's it. They don't need to be removed. That's why this is permanent. And then we have temporary. And I found some pictures online. So these look like needles that are injected on prostate. So that's what you've seen here. It's a treatment also for prostate. So you got one for prostate here that's permanent using seeds, and then you have one that is temporary. This involves the plantation of long needles into the prostate where there would be tumors. And you can use a higher dose with this in shorter time because it's not permanent. So here, the needles are removed after 5 to 10 minutes, and then you can do this again in a few days. So you can use a higher dose, but they are removed. They're not left in there. And that's it.